I've come up with 8 problems to go over from the textbook. 2 from each section we've covered so far. 12.1, which was on reflections. We have these 2 problems. Now, these are the only 2 that are out of order. I'll do number 55 first for 2 reasons. One, because it was actually an assigned problem of yours, so I'll do it before all the ones which I haven't done with you before. And number 2, I think it will help me explain number 36 a little bit more, because I'll go more in detail with number 55 with regard to the actual point reflections. In 36, I'll kind of be a little briefer with it. And then 12.2, numbers 35 and 39, 12.3, numbers 30 and 34, and 12.4, numbers 6 and 26. So these will be solutions to these problems, and I think they should be clearer as far as what your objectives are for these problems. Okay, number 55 in 12.1 for reflections. It gives you a point, A, which is on 2,4. And it asks you to reflect it across certain lines and give A prime, and then reflect A prime somewhere to give A double prime, etc. to triple prime, and quadruple prime. So the first thing we want to do is reflect reflect A prime across the line y equals x. And they do give this to you. And so now you should have a good example of what y equals x looks like. And it's for every 1 that I go in the x direction, I go 1 in the y direction. And it crosses the y-axis at 0. And crosses the x-axis at 0 as well. Okay, so here's that line, and we want to reflect this point over it. I can't really distort or rotate this entire image at all for you, so just tilt your head 45 degrees to the left, and kind of look at it straight up and down. So this is going straight up and down. Keep in mind that every single time you do a reflection, you're doing it straight across perpendicularly to your mirror. So you want to be looking at it like that. So whatever this reflection will be perpendicularly to my axis of symmetry, and that's what will be reflected on the other side. This one should look simple enough, saying I'm only one diagonal, or one square away diagonally from here, so I'm 1 square diagonally away from here. But there are multiple other ways we might have to attack problems like this, and I don't think I have to get into too much detail because I don't think I would present those problems to you necessarily. But it's still good to just know. And the one first thing that I do want to say is keep in mind that a perpendicular line means that it is the opposite reciprocal of that line. So when I'm looking across here perpendicularly, and obviously this will be my ending point, the slope of this line is the opposite reciprocal of the slope of this line. Now the slope of this line is 1, because the y equals mx plus b equation is y equals x, which means y equals 1x plus 0. M is 1, which is my slope, and b, my y-intercept, is 0. The equation of the line that has a slope that is the opposite reciprocal of this line and that crosses through the point 2, 4 can be described by solving it as follows. If the point 2, 4 means my x and my y, I can plug in 4 for y, and here keep in mind I'm going to write this in y equals mx plus b. I can substitute 4 for y. The opposite reciprocal of this slope, which is 1, is the opposite reciprocal, so negative 1 over 1. So my new slope for this line will be negative 1, times this x, 2, plus b. And that's how we can actually solve for b. So 4 equals negative 2 plus b. Add 2, b equals 6. What that means, and the new equation for this line, is y equals negative 1x, or negative x, plus 6. So what that means is that I have the equation of this line here that crosses through this point right here, and it would keep going up until it crossed at y equals 6 way up there, and it intersects at y equals x at a certain point. And we would like to figure out what that point was. Now, if you didn't have all these things to show that it's 3, 3, you might have to solve for it mathematically, and that's what I want to help you do. for a couple reasons, because it might show up in problems and because this is something you definitely have to know for Algebra 2. So here I have a system of equations. We have two lines, y equals negative x plus 6 and y equals x. This system of equations is such so that if I plug in some y value and some x value, they would have to equal each other, and there's only one value which that is true, which is obviously 3, 3. Now, we don't do trial and error. What we do instead is we can take these values and do what's called the addition-subtraction method. The addition-subtraction method basically takes these values. You can put a line underneath there and kind of add them together. If I want to add all the values together that are like terms, these x's can cancel out. So y plus y is 2y equals negative x plus x is 0, and then 6 is left over. So I have 2y equals 6. And I can solve for that and say that y equals 3, dividing by 2. And now I can go back into this equation, plug in 3 for y. So 3 for y equals x. Therefore, x equals 3. So what we solved for were all of the possible x's, x and y values that make this system of equations true. Basically, I can plug in these two values, 3 and 3, and that would make both sides equal for both equations. So that's a way of solving for the point of intersection right here if you did not actually have the visual graph or it didn't draw it to scale or something, which is 3, 3. Now this point is 2, 4, and its reflection over here, if I went 1 down, 1 over, 1 down, 1 over, recall what the slope was there. This is my A prime, and that point is 2, 4. So we found the coordinate point for that line. Now, I'm not going to spend as much time doing all the other ones just like that. That was just giving you a good rough example of what was going on. But I will keep in mind the slopes here, and this is something you really do have to keep in mind. When I went, when I counted how far away I was, recall like whenever we're reflecting across like the x-axis here. Say I wanted to do this and reflect it across the x-axis. Well, here's the x-axis. So I say, how far away am I from it? Well, I'm 1 unit away, and it's easy because I can just count up 1. So reflecting across would be on this side like that. And that's easy to do. And in most cases, this is easy to do as well. I can just count 1 square over diagonally like this because the slope is -1. But if the slope is different, let's say it were -2, then you'd have to go down 2 over 1, down 2 over 1. So you just have to know how slopes work. In this case, for -1, I went down 1 over 1, down 1 over 1. And when I do reflections over y equals negative x, like we'll do next here, I'm going to do the same thing. So let's find a double prime, the reflection image of a prime in the line y equals negative x. So let's take this point, reflect it across this line, and get our other point over here. So the way I want to do that is you look into the mirror perpendicularly, like so. Well, pretty much like so. And that slope ends up being 1, just like this. It should run parallelly to that. So if you wanted to write the equation for the line, you could, and you could solve for that. But as long as I find that actual slope, I think I'm in good shape. So let's count how many down 1s over 1s I need to do here. Down 1 over 1. 1, 2, 3. So that's the reflection. Now I need to go 3 more the same way. 1, 2, 3. And that is my reflection of this point right here. This is a double prime. And that's at the point -2, -4. You might be seeing a pattern already with these reflections and the numbers and such. Okay, that one is solved. Let's find a triple prime, the reflection image of a double prime, over the line, or in the line y equals x. So here's y equals x again. Let's reflect it across. Here's the perpendicular slope to it, -1. Again, that should look familiar. So let's go up 1 over 1. Here's the reflection. Up 1 over 1. There's a triple prime at -4, -2. I apologize if I am going quickly at this point. I think the first one